A friend of mine was asking me if I could make a circuit that would switch the LEDs on his plane on or off using his transmitter switches. And in this video, I'm going to show you step by step on how I made it. But first, let's see the basics. The very basic equipment of an RC hobbyist is a radio control transmitter and a receiver. As its name implies, it uses radio frequency to send data over to the receiver, and then it can be converted by the receiver to PWM in order to communicate to the equipment, for example, your servo or ESCs. As you may have guessed, the PWM signal is a standard command signal in the RC world. But before we delve into how to decode them, let's first see what PWM is. A PWM is a square wave signal with an amplitude V, a fixed period T, and a variable width W. The ratio between the width and the period is called duty cycle and expressed with D equals W over T times 100. And from then we can calculate the average output voltage of our PWM with V AVG equals D times V over 100. This technique is a very efficient way to vary the average voltage through a circuit, and also when combined with a low-pass filter, we can implement a cheap digital to analog converter, which means it takes a digital input and outputs an analog variable voltage. And we are going to take advantage of that property later on, as we will see. And now back to the radio control thing. It is a PWM signal that has a period of 20 milliseconds, a duty cycle between 5 to 10%, or a high time between 1 and 2 milliseconds. Assuming a voltage maximum of 5 volts, and according to the formula mentioned earlier, we should get an average voltage between 0.5 volts and 0.25 volts. So now let's measure it in real life with my FlySky receiver. So this is my transmitter. It has a switch over here that is hooked up to channel 3. And what happens when I flip the switch down, we have a duty cycle of 10%, and when I flip the switch back up, we get a duty cycle of 5%. So let's power our receiver and see what happens. Now we have our receiver powered and connected. I have some wires from the receiver, signal and ground, in order to measure the voltage according to the duty cycle. When I flip the switch down, I get an output of 0.355 volts. When I flip it back up, I get 0.180 volts. So why is that? Earlier we calculated 0.35 volts and 0.5 volts. So why do we get these wrong values? Well, that is because the MCU inside of my receiver uses 3.3 volts as a power supply. In order to alleviate that, I'm going to use a voltage translator so that we get a known amplitude and for a known output voltage. To solve our problem, I made this little voltage translator here. It is made of 2 transistors, and also I've already built my low pass filter here. It's got two 15 kilo ohm resistors two 2.2 microfarad capacitors. So now let's hook it to our DMM to see if it works. Now once again, the switch is in the upper position. We are getting 293 volts, and in the lower position we are getting 0.5 or 6 volts. So yeah, we are getting close. So now that we have our PWM to voltage converter, what do we do with our output signal? Well, that's when a component called comparator comes into play. This is an active component, so it needs power and ground. It has a positive input terminal, a negative input terminal, and an output. What this component does is that it compares two voltages at this input. For example, if the positive input terminal is higher than the voltage at the negative input terminal, the output of the comparator goes high. And if, on the other hand, the negative input terminal is higher than the voltage at the positive input terminal, the output of the comparator goes low. So now we need to hook up one of these inputs to our voltage output and get a fixed voltage at the other one. This is the circuit that I came up with. We have an LED here to indicate the state of the comparator. The positive input terminal is connected to our PWM to voltage converter, and a fixed voltage to the negative input of the comparator. Earlier, we've calculated that when the switch is in the lower position, we had 0.29 volts, and when the switch is when the switch is in the higher position, we had 0.29 volts, and when it's in the lower position, we had 0.5 volts. So let's say I want to turn this LED on every time the switch is in the lower position. So when the switch is at the lower position, we have 0.5 volts here. If we want to turn this LED on, the voltage here should be higher than the voltage here. So let's say we should have 0.45 volts here. To get this value, I used 10 kilo ohm resistor here and 910 ohms here. So I've put the circuit on the bench here. This is our comparator circuit, our LED. The receiver is powered and connected to the transmitter. So now let's test it. When I flip this switch, the LED lights up as we expected. When I flip it back up, the LED goes off. So yeah, we can now play with our little LED.
Wait a minute. That's it? That's the ending?
Of course, we could stop there and have fun with our little LED here. But I want to add something more practical, something more powerful than just an LED. So the solution to that is an electronic switch or the so-called transistor. So a transistor is an electronic switch. It can be controlled by the gate here, which should be connected to the output of our comparator. And we have our big load here between the drain and the power supply. So let's build it. So I've got the circuit built up here. We've got a transistor and this is my load. It's a 12-volt DC motor that is being powered by this LiPo battery. So let's get our transmitter. And as you can see, it's working. So that's how we make it